So I hope my screen is also visible. Uh, right. Yeah, so this is a rescheduled meeting. I was supposed to take this on Saturday, which I could not take. So thank you for joining this call. This will be a short one because it has only 7 questions in this, I guess. Yeah. So these are about decision trees. Yeah, so these are about decision trees. So let's get to it. These are the questions in the last run of this particular course, and I will be going through the questions one by one. Again, as always, if you have any doubts, you can stop me in between, or and towards the end, I will have a lot of time for questions, so you can ask me towards at the end as well. Okay, so which of the following properties are characteristic of decision trees? Low bias, high variance, lack of smoothness of prediction surfaces, unbounded parameter set. So, if you have gone through the course, if you have gone through the lecture, you would know that all these are low bias is definitely a correct option, and high variance is a correct option because if you if you give a decision tree the data and you adjust the training data and you don't prune it or do anything with it, then what it will do is it finally it can as well put just I mean separate out the particular region into in such a way that in every region only one point will come in the from the training data. That means it has low bias because it has a very low training error which can even go down to zero, and it has a high variance, which means again the same thing, that training error has gone down to zero. But now if your decision tree puts a single point in the entire region, that means that you probably won't generalize very well to the testing data, and therefore it has high variance. By the same logic, it will have a lack of smoothness of prediction surfaces because prediction surface for a decision tree is very difficult to imagine because it is not like you are learning some optimal hyperplane or anything, but you can think of like your if this is the region that you are working with, then decision tree can do something like this. Then it can so it can have multiple cuts here, multiple cuts there, and so on. And this can go on, and you can have arbitrarily complex such divisions of a particular region, and therefore your prediction surface. So finally, if you want to say that what should happen to my x1 and sorry to my x1 and x2 such that points lying in this particular region are of class 1, let's say, and the points lying in all the other different regions are class 0, then that definition of x1 and x2 becomes very difficult to, I mean, you can of course understand that this will be very difficult to note it down for even a two-dimensional case, and therefore it becomes very arbitrarily difficult when you have a very large dimensional space, and therefore the prediction surface is in general not very smooth. It will be very difficult to predict, it will be very difficult to define it in that sense, and therefore it is not smooth. Unbounded parameter set. This is so decision tree can have multiple parameters like it can have how many number of leaves that you have at the end of the decision tree. That can be a parameter that you want to choose. You don't want it to have too many leaves. You don't want to have too few leaves, and therefore that is a parameter that you want to choose. Then that is one way to so let's say this is your decision tree. This is your decision tree. So one way is you can want to limit the number of leaves that you have. The leaves I'm underlining here. The other is you can want to limit the number of you can limit the number of the levels of the decision tree that you want, the height of the decision tree that you want. So there are different such ways in which you can there are different such parameters associated with every decision tree. However, the number of parameters is not dependent on something, is not dependent on the what should I say? It depends only on the training data that you have, the training validation data that you have. It depends only on that. The number of nodes that a decision tree will have is can ideally be unbounded. If you want, you can have 10,000 nodes for a particular decision tree. If you want, you can have for the same data set, you can have 1 lakh nodes for the decision tree. So that depends completely on you and your choices and the training data. And therefore, there are no bounds to the number of parameters that the decision tree can have. And therefore, all the 4 options for this particular question would be correct. Hope this was clear. Then coming to the second question involves little bit of calculations. So I will just write the equation, and then the calculation you can do it offline. I've already done. I've checked it, and that should be. I mean, just doing the calculations itself is sufficient for your learning for this particular question. So you have some tabular data where these 3 or 4 other features, and you have something which is known as the target variable, which is malignant. And so what is the initial entropy of malignant? So entropy is, if you recall, entropy is minus pi log of pi, where pi is the probability of the number of classes. So here pi is 0 or 1. So I is 0 comma 1 here. So 0 comma 1 means the class index I'm writing. It is not that yeah, so class index, that is that the malignant can either be 0 or can be 1, and therefore I can be 0 or 1. So here if you see, there are 12 cases, out of which 5 are ones and 7 are zeros, correct? Therefore, the probability of class 0 is 7 by probability of class 0 is 7 by 12, and the probability of class 1 is 5 by 12. And so if you just insert this into these two things into the formula, what you will have is minus 5 by 12 log 2, this is log base 2, 5 by 12 minus 7 by 12 log base 2, 7 by 12. And if you do this calculation, it will come out to be 0.9798, right? Okay. So that is a simple calculation. Now for the same data set, what is the info gain on vaccination? So what does that mean? So that means that if you have a node, let's say, and if you have this node and you are splitting your data set based on the status of vaccination. So I'm denoting V for vaccination, and let's say vaccination can again be 0 or 1. So let's say when vaccination is equal to 0, I will put all the points into this particular node, and when vaccination is 1, I will put all the points into this onto the right node, right? So now let's check. So and yeah, so vaccination is 1 in this and these cases. So this and these cases. Okay, so when vaccination is 1, then you have this underlined, I mean the hyphenated cases, and when vaccination is 0, you have the star cases, right? So let me just put them as star. Okay. Now, so when vaccination is so let me fill out the left this particular note first. So when vaccination is 0, you see what is happening is there are 1, 2, 3, 4, 5. These are all stars. Why didn't These are all stars. Okay. Okay, vaccination is 0 in 5, 6, 7 cases, and vaccination is 1 in 5 cases. Now, out of the 7 0 cases which are here, you have malignant positive or 1 for malignant in 5 cases and malignant 0 in 2 cases, right? So this would be, I'm writing this as 5 positive and 2 negative. 5 positive means 5 ones and 2 negative means 2 zeros. I hope this is clear. Similarly, if you have vaccination of 1, then you see all are zeros, right? If vaccination is 1, then malignant is always 0 in all the 5 cases. So this has 5 negative. Okay. So this is the situation of the decision tree. This is the situation of the decision tree after you have split based on the vaccination variable. Now what you need to do is you need to find out the entropy here, because you are after information gain of vaccination. So you need to calculate the entropy here. You need to calculate the entropy. Yeah, I lost my internet connection. Am I audible now? And if you please confirm. Okay, cool. Okay, so what you need to do is, yeah, so you need to calculate the entropy at this stage, and you need to calculate the entropy in this in these two stages as well. I mean for these two nodes as well. And once you calculate the entropy for these two nodes, you need to take a difference. I'll show you how to take the difference of these two. I mean at the between the two stages, and that will be your information gain. So entropy at this stage is the same as the entropy that you calculated in the last question, because at this point all the malignant and all the non-malignant cases are together. So it will be 0.9798. Um, Entropy at this particular stage is easy to find, but I'll still tell it how to find this out. So out of 5 cases, there are 0 cases for which you have a positive. Out of 5 cases, you have 0 cases in which you have positive, and therefore this would be log 2 of 0, and 0 by 5, and this will be 5 by 5, log 2 of 5 by 5. So this would be 1. Sorry, this would be 0. Very sorry. This would anyway be 0, and this would again be, and this would again be 0, because log 2 of 1 is 0. Therefore it would be 0, right? Okay, so this part is done. The right hand node you already know. let's look at the left hand node. So I'll do the left hand node here. So left hand node, again, it's again quite simple. You have two positive, two negative and five positive. Therefore, you have 2 by 7 log 2 of 2 by 7 minus 5 by 7 log 2 of 5 by 7. So you will get some value here. So again, I'm not calculating the value. Let's say this is entropy of left. Entropy of left. This is the value that you have on the left node, and 0 is the value that you have on the right node. And in order to find the information gain, what you need to do is your initial entropy was this, and now your entropy is a weighted sum of the left node and the right node. Why a weighted sum? Because you see you have 12 data points here and you have 7 and 5 data points here, and therefore you need to weight your entropy of this of the left node by I mean, it should be multiplied by 7 by 12 because you have 7 points out of the 12 points here, and this needs to be multiplied by 5 by 12. That is anyway 0. So this would be minus 5 by 12 into 0 minus 7 by 12 into E left. Whatever this value would give, whatever E left would give, you multiply that by 7 by 12 and you subtract that from 0.9798, and that would be your information gain. That is the amount of information that you have gained in order to that is the amount of information that you have gained by splitting based on the variable vaccination. So if you do all these calculations, it will come out to be 0.4763. You can just check for yourself what this value turns out to be. It will be 0.4763. Okay, so these are the two problems in this particular assignment which had some um, maths involved in it, but yeah. So let's go ahead to the next problem. So the next problem is, consider the following statements. Decision trees are linear non-parametric models. Of course, this is false, right? Because linear trees can never be linear. They are non-parametric, that's true, but they have if then else conditions, like if x1 is less than 2 and x2 is greater than 5 and x3 is less than 7 and so on. So you can obviously understand that they can never be linear, and therefore the first statement is itself false. A decision tree may be used to explain the complex function learned by a neural network. This is one of the major applications of decision trees. I don't know whether it is still used now. Now this has been, I guess, replaced by linear networks. But introducing explainability into big complex models is something which linear decision trees. Okay. Actually, my net is very weak, so even if it will come, there is a lag between. Yeah, I guess it has come now. It is zoomed. I've zoomed in. Yeah. So it is hard to a decision tree may be used to explain the complex function learned by a neural network. So yeah, so that is the decision tree may be, so that is one of the applications of decision tree, and therefore statement 1 is false because decision tree is not linear. However, statement 2 is true. So that's fine. Then which of the following machine learning models can solve the XOR problem without any transformations of the input space? This is directly from the lecture. I guess linear perceptron can't solve it because you will need to learn a nonlinear boundary. Neural networks can solve any such problems. Decision trees again can solve this problem. Logistic regression can't solve this problem because logistic regression is primarily a linear function with logic. I mean, you get you get to convert the probability. You get to convert the output to a probability measure at the end. Then which of the following are the major advantages of a decision trees over other supervised learning techniques? Theoretical guarantees of performance is not there. Okay, that is not there. Higher performance, okay. Interpretability of classifier is something that we have seen. Higher performance is something that is not always true because neural networks generally perform better than decision trees. Therefore, higher performance will not be true. More powerful in its ability to represent complex functions is also not true because neural networks can be arbitrarily more complex than decision trees. So interpretability of the classifier is the only advantage that you have over other supervised learning techniques. Then consider a data set with only one attribute, which is categorical. Suppose there are q unordered values in this attribute. How many possible combinations are needed to find the best split point for building the decision tree classifier? The decision tree only makes binary splits like cart. Okay, so there are q such there are q such unordered values. So, okay, there is a lag from what I'm writing and what is coming on the screen. So let me wait for that. Internet is very weak here. I don't know. It's still not come on the screen. Am I still audible, or you can't listen to me also? Okay, but there is some issue with iPad. Then is it? Yeah, I think it has come now. So yeah, so no, I can't turn off the camera because the NPTEL people needs to know that I am the one presenting and not anybody else. So can't do that. Okay, so there are q unordered values. So if you have q unordered values in this way, then how many possible combinations are needed to find the split point? Binary, you are doing only binary splits. So binary splits means you are doing either like you are doing like this, right? I mean, depending on whatever value you choose here, you can split it into either the left part or the right part. So if there are q unordered values, then what you can do is you can put either uh, so how can I, yeah, so basically you can put this onto the left or the right. Every such unordered value can either go into the left part of the tree or the right part of the tree. Okay, it's lagging like anything. So basically, for every unordered values, you will have two options to either put it in the left node or the right node, and therefore there will be 2 to the power q options in total for the q unordered values. Now, if you look at for a decision tree, let's say you have some attributes. Let's say you have 10 attributes, and this 10 unordered values for these attributes, and you choose the first five goes into left, the last five go into right. That is one option. The other thing which you can do is the same first five, these they can go into right, and the same this last five can go into left. Both of these would basically mean the same thing for you and for a decision from a decision tree perspective, and therefore there, because of that symmetric property that you can, I mean, because of the symmetric property that I just described, you have to divide this by 2, because you don't care about which group of unordered values go into which direction of the node, as long as they're together. So 2 to the power q by 2 is 1. The other option is, but here one more thing is happening, like you can have all of them go into the left node or all of them go into the right node. You need to get out of that, because all of them cannot go into the same node, because you are doing a splitting, and therefore that particular splitting needs to be subtracted, right? Therefore 2 to the power q minus 1 by 2 to the power q minus 1 minus 1 is the correct option for this. Okay. Okay, so yeah, so that brings me to the end of this. Yeah, yeah, yeah. Yeah, go ahead. Yeah. Hmm. No, it won't. It won't come up, right? Because what you are doing is, let's okay. Let's say I'm taking a very simple example of you have one, two, three. These are the two values, and the other case is one and two. So what you can do is you can choose this to be left, left, right. You can also choose this to be right, right, left, right? These are two equally possible ways that you can choose. This by two comes simply because you don't want to take both of them separately. You just want a single, only one. Yeah, yeah. So if you have one, two, three, four, then you can have left, left, right, right. You can also have right, right, left, left. So these two things are not you are not considering them separately. The odd number, even number doesn't come here in that sense. Okay. Yeah. Any other questions? Yeah, I mean, I won't be covering any more things. So if you don't have any questions, you can leave. Yeah. Yeah, yeah, yeah. I'll do that. Let me see. Uh, I mean, I don't. Yeah, I don't know. I mean, these particular PDF files. I mean, whatever I work out in the class. Do you want those? I mean, that I'm giving again to the NPTEL people. Yeah. Class notes, I don't think you will be finding from us. Class notes you will have to take when you once you while you listen to the course. I mean, I understand that this course is a bit hectic for introduction to machine learning for the introduction to machine learning title, but uh, uh, yeah, yeah, I understand that. Yeah, 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 yeah. It's difficult, I know, but yeah, we don't have any notes per se, but yeah, you can take your own notes when you are going through the course material and we're going through the lectures. That would help. I mean, I can tell you, I have pasted the link of my YouTube channel. So I can tell you one thing that Introduction to Machine Learning course I have taken multiple times, not as a TA but as a student myself. This particular course is the most comprehensive introduction to machine learning course that I have seen, at least in India, what I have seen. Outside, I don't know, might be more comprehensive, but yeah, yeah, it's the, huh. No, no, this is much more. This covers much more. I mean, the breadth of this course is something which is it really amazes me how the professor also taught this course because in 12 weeks teaching this course is not an easy task. So it is a very comprehensive course. So that's why you might be feeling a bit overwhelmed with this course, but it's okay to feel overwhelmed with this because this is a comprehensive course. But it would be very helpful to you if you can go through the entire course and take your own notes and everything. That would be helpful to you in the long run itself. Yeah, yeah. I mean, yeah, it might be because I mean the you can just have a look at the you could have looked at the course content that would be covered in a course. Generally, this is very rare for a machine learning introduction to machine learning course to cover so many different aspects of machine learning that is generally never done in any courses. I mean, so this is but this is a very good course. You should stick with it and see. I mean, whatever advantage you get out of this course would only help you. So yeah. Any more questions? Okay, then if there are no more questions, I'll close the call. Thank you, everybody. Next Saturday, I would be taking. I mean, I was not well last Saturday. That's why I couldn't take the session. Next Saturday, I'm fine now. So next Saturday, I would be taking at the normal time from 7 to 9. I mean, 9, of course, it won't go up to, but I'll start from 7. Thank you, everybody. See you next Saturday.